Hi everyone, my name is Shihab and I chose intro and recap detection for movies and TV series as my topic for today. First, let's talk about the motives behind this research. Modern video streaming service companies offer millions of video titles for its customers. A lot of these titles have repetitive introductory and recap parts in the beginning that customers have to manually skip in order to achieve an interrupted viewing experience. To avoid this unnecessary friction, some of the services have recently added skip intro and skip recap buttons to their video players before the intro and recap parts start. To efficiently scale this experience to their entire catalogs, it is important to automate the process of finding the intro and recap portions of titles, especially in this modern day where people like to binge watch a whole season in one night. So, trying to skip the intro and recap manually can be really frustrating. We have there are several learning-based approaches that could be applied to tackle this problem. Two of those main approaches are the unsupervised and supervised approach. On the unsupervised end of spectrum, one could model intro and recap as different types of frequently repeating content and then try to use content-based matching to find them. Although an advantage of this approach is that it does not require labeled data for training a parametric model, it does pose several practical challenges. It does pose several practical challenges. First is its false positive rate can be high due to multiple segments of shared content between two or more episodes. While one could apply a Dolic rule-based filtering scheme to remove some of these false positives, such solutions only address a subset of these errors and are difficult to generalize. Second, this approach requires multiple episodes before the content in different episodes can be matched. When there's only one episode available in a TV series that usually premieres every week, this approach will be really not applicable. Similarly, this approach cannot be applied to movies given their single-tone nature. Third, this approach does not work well for titles where the intro content changes for each episode. The alternative approach that does not pose the aforementioned limitations is to view the problem from a supervised learning perspective. An underlying assumption in supervised methods is that there are some frequently occurring patterns between the features, which are the video contents, and the labels, better known as intro and recap timestamps. The fact that humans can identify whether the content is intro, recap, or the actual content suggests that there are discriminable intro and recap patterns in the titles. Looking closely at the title data gives some clues regarding the following common patterns. For intro, mostly it shows the title credit information displayed on background with the silent transition period, whereas for the recap, it's usually a series of rapidly changing scenes shown, opening sentence, music playing in the background. So let's talk about the key challenges here. First one is how to best formulate the intro and recap detection into a supervised learning problem. The more obvious choice of formulating it as a regression problem with video as input and intro and recap timestamps as regression targets is likely to give suboptimal results since the transition among intro, recap, and the actual content will not be explicitly modeled. The detection approach is trainable end-to-end and therefore easy to maintain at scale. They usually use convolutional neural networks, or better known as CNN, to extract discriminable visual and audio features from video titles. These features are then fed into a bidirectional long short-term memory, which is called BLSTM network, to capture the various long and short-term dependencies among different frame features. Finally, for optimal temporal smoothing, they use a conditional random field CRF to jointly optimize the labels of all video frames. Second challenge is what's the best way to characterize these different patterns in the model. I think that one way is to build an individual detection model for each of these patterns. For example, a model to detect white text on background, while another to detect if music is playing. However, to ensure high coverage of intros and recaps, such an approach requires a large list of known patterns, which is time consuming to identify, and thus such a list is not likely to be comprehensive. Let's say there was such a comprehensive list available. It will still be expensive to build a model for each enlisted pattern and practically difficult to maintain them. This approach allows them to model multiple information channels in a unified manner. We present a detailed empirical analysis of how multimodal fusion performs for the problem at hand with both early and late fusion schemes. Final challenge here is how to leverage the discriminating patterns existed in different data modalities. We need to use multiple data modalities effectively, and it's unfortunately unclear how to optimally do that for this problem. This framework is applicable to both the intro and recap detection problems and can be extended to other types of video segments, example end credits. This solution is easy to put into production since its interference does not depend on preceding episodes, thereby reducing its memory requirements and maintenance overhead. Right now you can see an illustration of the sequence labeling for intro and recap detection problems. Each of the two consecutive blue bars represent a time interval of a title. The labels above demonstrate the type of the interval, where R represents recap, I represents intro, and C represents actual title content. Right now you can see the model architecture, which is an overview of their network architecture. Here, blue vertical lines represent the video frames, while the orange and green bars represent the visual and audio features of the corresponding frames respectively. Letters R, I, and C correspond to recap, intro, and actual title content respectively. Here are the three approaches applied together, fused together for one approach, where CNN is used for visual and audio feature extraction, BLSTM for capturing long and short-term temporal dependencies among various frame features, and finally CRF is used for joint label optimization of video frames. We can see from this table that the proposed method has significantly better performance than the alternative approaches that frame intro and recap detection as a temporal action localization problem using visual feature. We can really see the gradual increase in the precision and recall for both intro and recap, where you can see at the bottom of the table how it increased to 63% for precision in intro and 56.79, almost 57% for recall, and the same goes for recap. This is a massive increase in numbers. In this table, it shows the performance of the proposed method, which is BILSTM plus CRF, on the validation data set with 1 second tolerance using different types of feature, namely audio, visual, early fusion, and late fusion of audio and visual features. We can see that the early fusion results in the best model performance among the 4 types, indicating that our architecture has the capacity to model both the visual and audio feature well when they are fed to the model as inputs. And you can see here now we are at the last part, which is the conclusion and future work. In this research, they used the CNNs to extract visual and audio features, then fused the features into BLSTM to capture the context change among consecutive frames, and finally used CRF to jointly optimize the sequence labeling for intros and recaps. They demonstrated that this model can achieve high accuracy and perform much better compared to several other deep architectures. It has been shown that the BLSTM and CRF components were critical to get high accuracy, and the fused features generally perform significantly better than audio or visual features used independently, especially when BLSTM and CRF are used. The approach can be extended to detect other video content, let's say end credits, and can also be applied to other sequence learning applications. Going forward, I read that their plan is to experiment other ways of visual and audio feature fusion to improve detection accuracy. Moreover, caption information is not incorporated into this model due to its limited coverage, and their plan is to explore ways to overcome this data limitation to enhance their model. That's it, and thank you all for listening. Goodbye.